going to continue here. So the normal sequence is you look metathesis. Is there a metathesis reaction? If no metathesis, then we'll look for acid base. If there's no acid base, then the last possible type of reaction would be redox. Sometimes we'll jump straight to redox at the end, but there are a number of redox methods that we're going to do. The first one is, this is reaction type 3A, is the element plus element. The element plus element is a combination reaction. You recall, I don't like the word combination, but you know, for redox it's okay. Element plus element combination. And so, for example, magnesium. If I take magnesium solid and oxygen gas, what forms? Magnesium oxide. And what's the formula for magnesium oxide? Magnesium oxide would be okay, it would just be magnesium. It's going to be a 2 plus, oxide is going to be 2 minus, so it's just going to form MgO solid. In this case, there's no water around, it's just a solid and a gas. To balance this, I'll either put 1/2 here for 2 magnesium solids plus an O2 gas yields 2 MgO solids. This is the reaction we did in the lab. Remember when we took the strip of magnesium and burnt it in air? This is it. Let's try another one. Copper plus O2. What are we going to form? Well, here we have a problem because magnesium, we only have one cation, but copper it's either going to be copper plus or copper 2 plus. So which one is it? Well, let's say you have a penny, and the penny is oxidized. By oxygen. What happens is the first one that forms is Cu2O solid. You know, so if you look at penny and its gradual oxidation, it kind of turns a slight red color, or reddish color. It's copper 1 oxide. Let's look for some more images so we can see the different color variations. You know, that's in powdered form. That's all red, yes. And so first your penny kind of turns a red color, red-orange type color. And then eventually it goes to a CuO solid. What color is CuO solid? Let's see. Let's take a look at CuO. And then it goes to a black color. Do you see that? And so the pennies, as they age, they'll go from red. They'll start off with more orange and then go to red-orange to a black. And that would be copper 2 oxide. And so very, very old pennies will be black on the surface. And so we have multiple products possible, so it depends on which one. So maybe we'll just do the complete reaction here, an old penny. So we see solid plus O2 gas. This can yield, both products are possible. So we have, when we have variable charge, then we can make multiple products. In this case, we'll just make CuO solid. So again, we'll need a 1/2 here to balance it out. Or if we go to Cu2O, this would happen first, this would happen second. This would be complete oxidation. We call this complete oxidation. This one is incomplete oxidation. That is, it could be oxidized further. How would you balance this one, though? We'd need 2 coppers and 1/2 O2, then it would be balanced. Or double the whole thing. You could double it. So we got a complete oxidation and incomplete. Actually, can we go for even more complete? Copper is 1, 2. Is there copper 3? Do you recall? No. This is about it. Let's get a stop there. Iron. Iron is what's the charge on iron? Iron is a 2-3. So when we have complete oxidation of iron, it goes to iron 2 oxide or iron 3 oxide? Complete oxidation of iron would go to iron 2 oxide or iron 3 oxide? It's an iron 2 or iron 3, right? Complete, that means we're going to strip away all the electrons. If we strip away all the electrons that we can, is it +2 or +3? We'll call it complete here. This would be incomplete. So iron oxide would be incomplete. This is iron 2 oxide. And then complete oxidation would be iron 3 oxide, which is Fe2O3. And for this one, we'd need 1/2 O2. For this one, we would need 2 irons and 3. 2 irons and 3 halves of O2. Yeah. So we could double the whole thing. This would be complete oxidation. This would not be complete oxidation here. Typically, we could do complete or incomplete, whatever. Let's take a look at some images. Iron 2 oxide has this color. So when you see rust, rust is iron oxide. When you see rust, is rust black? Like this? That's iron 2 oxide. Or is rust kind of this red-orange color. This is iron 3 oxide. What color? Red-orange, right? Rust is red-orange, red color. And so what we see with the iron is, you know, it doesn't stop here. Eventually it gets completely oxidized here. Seeing complete oxidation. So when we're doing element plus element, for some they're fixed charges. This fixed charge is okay, but for others it's variable charge. So we can have different products formed depending on how complete the reaction is. Okay, B, complete combustion. Complete combustion. So, for example, if I burn methane and I want to burn it completely, what does it form? Well, that's methane, CH4 gas plus O2 gas. That happens in the burner here. What forms? With complete combustion. CO2 and water. CO2 is a gas. What about incomplete combustion? If I have incomplete combustion, I might, instead of forming CO2, I might form what? Carbon monoxide. Because carbon can be all the way to 4 plus 4. So carbon monoxide or soot, the black particles that we generated in the lab the first day. I talked about this in the first lab period. Incomplete combustion and complete combustion. How come? When we get incomplete combustion, if I'm generating soot and carbon monoxide, it must be because I don't have enough, what? Oxygen. So I need more oxygen. In other words, it depends. The same thing here. You know, if there's plenty of oxygen, I should get complete oxidation. If there's plenty of oxygen, I should get complete combustion. So let's balance this one out. When a balancing complete combustion of carbon, hydrogen, and oxygen containing compounds. Carbon, hydrogen, oxygen, what we call these are organics, organic chemicals, yield CO2 and water. They all yield the same product, CO2 and water. And so let's go ahead and balance this. Balancing this, we've got to balance by atoms. We can't balance by ions like in metabolism. 1 carbon atom, 1 carbon, 4 hydrogens. We only have 2 here, so I'll do double. Make 4. And that gives me 2 plus 2 oxygens, 4 oxygens, so I'll need 2. Then it's balanced. It could be a carbon, hydrogen, oxygen containing compound. So we could also burn sugar. Let's burn glucose, C6. H12O6, this is glucose, which is a solid. If we burn glucose, what forms? Well, we burn it with oxygen, and what forms here? The same products. What are the products? CO2 and water. Now we'll have to balance it. Okay, so we have 6 carbons here. We need 6 CO2s over there. How many hydrogens? 12 hydrogens. And then oxygens. There's 6 here. Well, we are not going to touch that. So we got 12 plus 6 is 18 oxygens. So we need 6 plus 12, right? To get 12, I'll have to multiply that one by 6 also. So that would be the combustion of glucose here. So it could be carbon, hydrogen. It could be alcohols too. Ethanol is the same thing. If I burn alcohol, I'm going to get CO2 and water. That's combustion, complete combustion. Okay, the next type of redox reaction that we're going to do, this is for complete combustion of organics. The next type of reaction we're going to do is something called the signal replacement. A plus BX pattern. A plus BX yields AX plus B. Then we have the X2. X2 plus AY yields Y2 plus AX pattern. Plus exceptions. So there are two single replacement patterns, plus there's exceptions that must be memorized. So if we have something like this, like Zn solid, this is our A, plus HCl aqueous, this is our Bx. So A is going to be an element, Bx is a compound, so it's an element plus a compound. Okay, when I look at this, what forms here? Well, I have A plus Bx is going to yield AX. A, so we're going to go from element A to cation A. And so zinc forms what charge or charge is. Only the two. Zinc is fixed charge. It only forms Zn2 plus. Chloride's going to form Cl minus, so the formula is going to be ZnCl2 plus H, but H alone is not stable. In order to make it stable, we need to go H2. So this is going to form AX plus B. Now we got to determine driving force. Metathesis driving force and acid-base driving force do not apply. Do not work. We have to use the redox driving force. In this case, we're going to look at the activity series. For signal replacement, use activity series. This here is an inverted activity series here. Lithium we say is the most active, and then it goes down. Hydrogen is less active. It's less and less. Copper is less active. Silver is less active. So lithium is the most active. So it's flipped upside down. Take a look at this activity series here. Lithium, copper, silver. If you want, you could use the activity series in your book. Looks like this, where they flip it right side up. And so the most active is lithium. Then it goes down. Here's copper, silver. So for single replacement, use activity series for A and B. Driving force is going from more active to less active. More active to less. Here, lithium is most active. And so what we're going to do is we're going to compare A and B. A is zinc, B is hydrogen. Lithium is most. So if lithium's most, then zinc is here, hydrogen's here. Which one is more active, zinc or hydrogen? Zinc, more active. So in this case, we're going from the more active element to the less active element. So this is more active. This element here is less active. So if we're going from more active to less active, we say that this driving force is present. Therefore, we should have reaction. Or if there's going to be reaction, we'll balance it. To balance this, we just need two HCl's. Then this is aqueous, this is going to be aqueous, this is going to be gas. So we do have gas formation, but I can't use that as a driving force because this is a redox type reaction. Gas formation does not work for redox, even though I have gas formation here. What works for redox is, in this case, going from more active to less active. Therefore, I have reaction. If I look at this chart, the chart I posted on Piazza, it's just upside down here. So if I look at, here's zinc, here's hydrogen. So zinc is more active, it's closer to lithium. Next example I'll do is chlorine plus potassium bromide. Solution. What's the formula for chlorine? Cl. Is it stable alone like that, or does it like to form diatomic molecules? Chlorine, the element, stable, or does it like to form diatomics? So chlorine's going to be Cl2. What's potassium bromide? KBr. So do I see this is an element, which we call A, and a compound, which we call Bx. This is an A plus Bx type reaction. But it's wrong. This is not an A plus Bx type reaction. You know what it is? This is the wrong pattern. This is the X2 plus AY pattern. It's the X2 plus AY pattern. If it's the X2 plus AY pattern, what forms? Y2, which is Br2 plus AX KCl. And then what we're going to do is we're going to compare X2 versus Y2. What we want to do is we want to go from more active to less active. Do you see it on this chart here? No. If it's not on the chart, does it mean it doesn't exist? No. It just means the chart is a bridge. This is a different type of reaction altogether. We're going from more active to less active on the opposite side. This is one of the exceptions. There's one more exception we'll talk about. And that is when X is not a spectator. The other exception is when X is not a spectator. I shouldn't say the other, another exception. Another exception is when H2O liquid reacts. And so you have to memorize some exceptions here. What's the easiest thing to do? The easiest thing to do is not have to memorize any exceptions. By controlling what you see. You don't have to worry about any exceptions as long as we're very careful about what we give you. As far as problems go. And so, if I were to never test you on any of the exceptions, then you don't have to memorize any exceptions, right? So as long as you know there are exceptions, then you're okay. So the advantage of single replacement, so what you should know is this. A plus bx yields ax plus b. So the advantage of this is simple pattern. The disadvantage is it doesn't always work. Because of the exceptions. predicting redox. Therefore, I have an alternate method that we can use. That does not require one to memorize exceptions. This alternate method is not in the book, though. But it's not difficult, so we're going to talk about the alternate method right now. I call this the consult the redox chart method. So let's take a look at the redox chart method. At the top left, what is that? F2, what's that called?
Fluoride.
This is called fluorine or fluoride?
Fluoride.
Top left. F2. This is called fluorine gas. Fluorine gas. What is fluorine gas doing? Is it taking electrons or giving up electrons? Taking electrons. And so do we call it an oxidizer or reducer? Do oxidizers take electrons or reducers take electrons? Oxidizers. This is at the top of the chart, and so if it's at the top of the chart, we say it's the most powerful. Most powerful oxidizer. And so fluorine gas is the most powerful oxidizer. What's the least powerful oxidizer? The least powerful oxidizer is there at the bottom of the chart. What do you see at the bottom of the chart? Lithium plus. Does lithium plus really want an electron? No. So that's why it's least powerful. Lithium ion plus an electron. This is the weakest oxidizer on the chart. And so we have the strongest oxidizer on the chart, fluorine. The weakest oxidizer on the chart is lithium ion. Now, this chart is a dual chart because this chart is both a chart of the oxidizers on the left and a chart of the reducers on the right. So for example, each of these can go both ways. So if I go forward, fluorine's gaining 2 electrons to make 2 fluorides. That's going forward here. If I go backwards, fluoride is losing electrons to form fluorine. And so that's what we call the species that loses electrons is a reducer. And so this is fluoride. Fluoride is the least, I shouldn't say least, I'll just say fluoride is the weakest reducer. Why is fluoride the weakest reducer? Because fluorine doesn't want to lose electrons. Fluorine works hard to take the electrons. Once it takes the electrons, it keeps them. It doesn't let go. So fluoride is the weakest reducer. However, does lithium ion work very hard to get electrons? No, it doesn't. And if it gains electron, it will form lithium metal. So lithium metal, or lithium solid, does it really want that electron? No, it doesn't. And so lithium metal is the most powerful reducer. It's the most powerful reducer. And so this chart is a double chart. Where, on the last chart we looked at, where was the strongest acid? Strongest acid is what? HClO4. But ClO4 minus is what? A base. Is that a strong base? It's a weak base. In fact, it's the weakest base. The strongest base is way at the bottom. And so this is a chart of acids on the left, the strongest being at the top left, and bases on the right. The strongest base is at the bottom right. That's called conjugate pairs. We have conjugate pairs in redox too. This is a chart of oxidizers. The strongest oxidizer is fluorine. The strongest reducer is lithium. See how it's inverted like that on the opposite end? So it's fluorine and lithium. And so this is the chart. And so let's take a look at the oxidizers, see if we can name the oxidizers. Can we name them? The strongest is fluorine. The next would be, you know what O3 is called? O3 is called ozone. Ozone. And we need, what's H plus called? H plus is called acid. We need ozone and acid. What's next? This one you don't know. This kind of looks like disulfate, but it's not. That's 2O82 minus. Leave it there. You should know this one. What's this one called? Yeah, hydrogen peroxide. It's called. You should know this one. What's this called? Permanganate. Permanganate in acid, or H plus acid. What's this one called? Lead oxide, but they're two. Is this lead 2 oxide or lead 4 oxide? This would be lead 2 or lead 4 oxide? This is lead 4 oxide. This is lead 4 oxide in acid. What's this one called? Chlorine or chloride? Chlorine. This one? Dichromate, good. Dichromate in acid. This one? Manganese 2 or manganese 4 oxide? This is manganese 4 oxide in acid. You should know this one. O2 is called oxygen gas in acid. This one you should know too. IO3 minus. What's that called? Iodide with a D? No. Iodide is I minus. This is IO3 minus, which is called iodate. Good. Iodate in acid. This is bromine or bromide? Bromine, this is bromide. So bromine, this would be nitrate in acid. Nitrate in acid is called nitric acid, so that's nitric acid. It could be nitric acid, but it doesn't have to be. It could be any source of nitrate, sodium nitrate, and any source of acid. Any source of nitrate and any source of acid will make this mixture. This is silver ion or silver 1 ion? Silver 1 or silver? Do we need the 1 or we don't need the 1? In other words, I'm asking you, is silver fixed charge or variable charge? Fixed charge. That's a silver ion. Is this iron 3 ion or just iron ion? Is iron fixed charge or variable charge? Variable, so this is iron 3. This is oxygen in, didn't we see oxygen and acid? Here, oxygen in acid. This one's oxygen in acid. Why are we, this is deja vu. Why are we saying it twice? Because they form different products. This oxygen and acid, what is it? Here. This oxygen and acid forms water. This oxygen and acid forms hydrogen peroxide. Which one's a better product, water or hydrogen peroxide? More stable. Water. And so this is better. And it makes sense this is better. This is the stronger combination. So as long as we have enough acid, this should be it. So the strong. All these are called strong oxidizers. Now we're going to get to more moderate oxidizers. The strong oxidizers. Let's look at some more moderate oxidizers like this. What's this called? Copper 2 ion, Roman numeral 2. This one's called sulfate in acid. Sulfate in acid. The sulfate can come from any sulfate salt, like sodium sulfate, or it can come from sulfuric acid. If it comes from sulfuric acid, it'd be HSO4 minus rather than this. But anyway, the sulfate in acid is a moderate oxidizer. This one is tin 4. This one is sulfur in acid. This is just H plus acid. Acid's an oxidizer in itself. This is lead 2. These are the moderate oxidizers. Now we're going to go to the weak oxidizers like this. This is tin 2. So tin 4 is a better oxidizer than tin 2. It makes sense. Which one do you think wants electrons more? Tin plus 4 or tin plus 2? Which one wants electrons more? Tin plus 4. Why? Why would tin plus 4 want electrons more than tin plus 2? What charge are electrons? Minus. What charge is tin? Plus. So which one wants more? Plus 2 or plus 4? Plus 4. Why? Because they want more, because why? They're higher what? Yeah, higher charge, higher positive charge. We see the same thing here. Iron 2 versus iron 3. Which one wants electrons more? Iron 2 or iron 3? Iron 3, obviously, because it's higher charge. This is Coulombic attraction, Coulomb's law. That's part of it. Then we have, what's this called? Is zinc variable charge or fixed charge? So is this zinc Roman numeral 2 or just zinc? Just zinc. Aluminum, a fixed charge or variable charge? Fixed charge. So aluminum ion, magnesium ion, sodium ion. calcium ion, potassium ion, lithium ion. Lithium ion is what is lithium ion? The strongest oxidizer, weakest oxidizer, strongest reducer, weakest reducer. Lithium ion is the weakest oxidizer. However, lithium metal is the strongest reducer. Are lithium ion and lithium metal the same thing? No, they're not. They're not the same thing at all. Just like is sodium metal the same thing as sodium ion? No, they're not. So let's see, are we out of time? Yes, we're out of time here. So we'll look at the reducers. The most powerful reducers are all metals. Do you see that?